and welcome to Astronomy 100. In this video, what we're going to do is start to put together the whole concept of orbital mechanics. In previous videos, we've been able to work out all the bits and pieces. And as I promised when we began all of this, is that the concept of orbital mechanics is one that is, well, it has lots of parts to it. It's not just one simple explanation. And if you think about what we've talked about Newton's 3 laws, and make sure you understand them individually, because we're going to put them all into the pot, into the recipe, if you will. We've also talked about the universal law of gravitation, which is obviously an important part of this as well. And then in the last video, we talked about what it means for bodies that are falling, what it means for a falling body, and the acceleration of that fall. And remember, the idea is that all bodies fall at the same rate, regardless of their mass. So what we're going to do is, it's time to put everything together. And to put it all together, let's start with something that actually Isaac Newton did in a very, very kind of an ingenious way to be able to get the idea across. Let's go ahead and get started here. So Isaac Newton comes along, and Isaac Newton is able to say that when it comes to orbiting bodies, it really, again, has to do with falling bodies. And what we're going to do is put all the pieces together, but we're going to do it in the way that he did it. And let me show you, again, this is his exact analogy. This is 350 years old or thereabouts. And I'm going to show you precisely the way that he gets the point across, because it turns out the way that he describes this is perfect. It's very easy to understand as long as you follow the bits and pieces. So Newton says, let's imagine a big table, and on the edge of the table we have a cannonball. You'll find out why in a minute, why it's a cannonball. And of course, if we were to just kind of go right behind the cannonball and just tap on it, it would of course fall to the ground. And of course, as it falls to the ground, it takes a second or two before it hits the ground. And remember, this is the acceleration of the cannonball due to gravity. Gravity is the force pulling on the cannonball, and the cannonball, of course, is trying to go to the center of the Earth. The ground just gets in the way. Now Newton says, what if we were to back the cannonball to the middle of the table? But this time, instead of just tapping it, we're going to give it a push. And so the push means it's going to roll along the table, and by the time it reaches the edge of the table, it's going to once again fall. But from experience, you know that once it hits the edge of the table, it's not going to fall straight down because it has a speed to it. Because you gave it a push, the rolling action of the cannonball means it's going to hit the edge of the table, and it's going to go out as well as down. So out combined with down creates this curved path, and we're going to give that a name. That curved path, we're going to call it the trajectory of the cannonball. So the cannonball has a speed, and it drops as well as goes out, and you combine those two, and you get the white curved trajectory that you see here. Now Newton would say, let's do it yet one more time, but this time we're going to do it from this edge of the table, and we're going to push and push and push and push and push so that by the time it reaches the edge of the table over here, the cannonball is going even faster than it was the last time we did this. Now the results are very similar. The cannonball is going to roll across the table faster and faster and faster, and then finally reach the edge, and it will also have a trajectory. But the difference is, instead of landing right here, it's going to land right here. In other words, the faster speed makes it go further down range. As it falls, it also goes further down range, and it hits the ground right there. Now, these are all things that you probably would imagine, or heck, you've probably experienced this by just simply throwing things or dropping things, sports, whatever. Now, Newton says, let's take the cannonball and let's move it to the top of a very, very tall mountain. And I realize this looks ridiculous, because it is. There are no mountains on Earth this tall. But he even emphasized, let's go to a ridiculously tall mountain. And in this case, instead of pushing the cannonball off a table, what we're going to do is actually fire the cannonball out of an actual cannon. Now before we do this, here's what I want you to notice. Notice the cannon is oriented horizontally. So in other words, it's not pointed up, it's not pointed down, it's pointed level with the ground, or horizontally. When the cannonball gets fired out, notice the direction of the cannonball comes out of the horizontal cannon, comes out horizontally. It's at this point, though, that gravity, of course, is always at play, and so gravity is going to make the cannonball fall as well as go out. So let's back up a little bit. And so when we shoot the cannonball, what we notice is it's going to come out of the cannon and it's going to have a trajectory because it's got a speed and it's being pulled on by gravity, it's falling, and it ends up hitting right here. These people in this country never even knew what hit them. It came out of nowhere. So this cannonball falls, but it follows a trajectory as it falls to the ground. So Newton would have said, let's do this one more time and let's put more gunpowder. So we're going to make it so that the cannon is going to really shoot the cannonball out even faster than it did for this one. Now, as you can imagine, with more gunpowder shooting the cannonball out faster, it's going to change the trajectory. Just like on the table experiment, you can see that the cannonball is still going to come out, but it's going to actually have a new trajectory that's going to fall and fall while it travels outward, and it ends up hitting right here. Now, it's at this point what I want you to notice is, notice the trajectory of the falling cannonball. It is starting to curve very much like the curvature of the Earth. So the trajectory of the cannonball is starting to get closer and closer to mimicking the curvature of the Earth. So Newton says, finally, what if we put just the right amount of gunpowder in so that when we shoot the cannonball out, as it falls, while also going outward, so outward plus fall, will make the trajectory of the falling cannonball become equal to the curvature of the Earth. And what you'll notice is, at just the right speed falling around the Earth, the cannonball's trajectory is going to miss the Earth. And of course, it's kind of dangerous because it comes right back. Now, what you are actually seeing is that the cannonball is in orbit. What is absolutely critical is to understand that an orbiting body is a falling body. What is different than just falling to the ground is that you have a speed that is outward while you simultaneously fall. So if that speed outward is the appropriate speed while the Earth pulls on the cannonball, the curved trajectory, when you combine those two, will be so that the cannonball misses the Earth and continues to go around and around and around. And as long as there's nothing to stop the cannonball, it will just keep going and going and going. Think back to Newton's laws in the previous videos. Remember, Newton's first law says that an object in motion continues in motion in a straight line at a constant speed unless an outside force stops it. So if the cannonball has the falling action of what you see here, as long as there's no outside force to slow the cannonball down, it will just continue to fall. So it would be obeying Newton's first law. All orbiting bodies are actually falling bodies. The moon falls around the Earth falls around the sun falls around the galaxy. Now, obviously, what the critical ingredient is the speed in this direction is the appropriate speed to allow the falling body to miss the Earth. So that's what Newton then pondered, is what is that appropriate speed. Now, to tell you what this speed is, let me show you the concept. It's called orbital velocity. And remember that velocity is speed plus direction. What we're really interested for this part here is just the speed portion of velocity. So orbital speed is what we're after. Now, orbital velocity is equal to gm over r, and then you take the square root of that. The m is the mass of the body that you're orbiting. So if we're orbiting around the Earth, m would be the mass of the Earth, and r would be how far from the center of the Earth to whatever height or elevation or altitude you want to orbit at. And I'll make that more clear in just a minute. Now, the m is a known value, the g is a value that we know, and the r is a value you can plug in. So you can actually calculate what is the minimum speed necessary to orbit the Earth, because all of these have regular numbers. And when you do that, what you are calculating is the minimum orbital speed for the Earth, and it turns out to be 17,500 miles per hour. In other words, you would have to shoot a cannonball out of a cannon at 17,500 miles per hour for it to orbit the Earth, to be able to go outward and fall without ever hitting the Earth. Now, 17,500 miles per hour, that's a number that's very, very big, and it's hard to put it into context. So let me try to help you with that. Let me give you some comparisons. This speed, 17,500 miles per hour, is 5 miles per second, just doing the math. So in other words, for 1 second of traveling, you go 5 miles. So imagine if you're commuting back and forth to Temecula, to the campus, or from one city to the next. Can you imagine going from the city of San Marcos, where Palomar College is, to your home in Temecula, and it only takes you maybe 4 seconds or 5 seconds to get home. So we're talking enormously fast, 5 miles per 1 single second. The other way to look at this is when it comes to military airplanes, there's a way to quote the speed of that military airplane, and it's called the Mach number of the airplane. Mach 1 is the speed of sound. It's about 700 miles per hour. So some military airplanes can go Mach 1, and that's breaking the sound barrier. Now Mach 2 would be twice the speed of sound. The fastest military vehicles today, well, that's classified, but the military will admit to speeds of Mach 2 plus, meaning that faster than twice the speed of sound. An example is the SR-71 Blackbird, a spy airplane from the 1960s and 70s, is rumored to approach Mach 4, 4 times the speed of sound. Now, what is the Mach number for orbital velocity? Well, it's Mach 25. So in other words, to be able to travel at orbital speed, an airplane would have to go 25 times the speed of sound. And there are no airplanes that can travel that fast. They're not even close to that. So the ability to orbit around the Earth is not something that airplanes can do. They're just not built for that purpose. But we obviously have had the ability to orbit around the Earth. We're quite successful at that. And there are vehicles that are built specifically for the reason to orbit around the Earth. And these vehicles, the one requirement to be able to orbit around the Earth is to be able to travel at 17,500 miles per hour. Now, what I'm going to show you is an example of doing this very thing and orbiting the Earth, and we'll talk about the bits and pieces that go with that. But we're running a little short on time, so we're going to save that for the next video. I hope you'll join me.